So today we will be presenting the dynamics of charged and neutral allied added atoms and dimers in graphene 6.0 carbon nanotube and graphene hybrid. Hi, I'm Brandon, and together with my groupmates Sean and Dennis, we will be presenting the findings of our research. Okay, so the context of our experiment is the lithium-ion battery. There are a few advantages to it, namely it is rechargeable and has high energy density. This means that it can produce a high amount of energy for its net weight. However, there are certain areas to improve on it, and this includes the charge and discharge cycle and the level of energy output. Next, it would be our solution to that problem, and that would be to use the carbon nanotube as a path between the anodes and the cathode of the battery. In this experiment, we will be investigating if the carbon nanotube graphene hybrid would help to speed up the diffusion of the lithium ion. Yes. And right now, this is how the lithium-ion battery works, where the lithium ions would travel from the positive electrode to the negative electrode while carrying energy along with it. Okay, so the aim for this experiment would be to investigate the diffusion of lithium. The activation energy barrier, which is the amount of energy that is required for the lithium to travel through the graphene nanotube. The minimum energy path, which is the path that requires the least amount of energy for the lithium to diffuse through, and the charge density, which would be the amount of energy that is required per unit weight of the lithium. All calculations were performed using a plane wave basis set. The ultrasoft Vanderbilt pseudopotential was used with a cutoff energy of 25 Rydbergs, and energy density cutoff of 200 Rydbergs. The Mazzari Vanderbilt smearing method was used to aid convergence with a smearing width of 0.001 Rydbergs. A 4x4x1 Monkhorst Park grid was used for Brillouin zone integration. All parameters were sufficiently tested for convergence. Calculations for diffusion dynamics employed the nudged elastic band theory.
The first set of calculations we carried out was lithium diffusion on graphene. So what we found out was that lithium actually has a low activation energy when it diffuses across graphene. This is quite easy. Yeah. Another thing we found out was that after we simulated the neutral system, we simulated a charge system where we had electron localized on this system. Then what we found out was that actually the activation energy was lower than that as compared to the neutral system. And after that, we tried simulating the systems with dimers and dimers in this orientation. Then what we found out is that dimers act as though they were one atom, and yeah, there's no difference if it's a dimer. So after simulating lithium on graphene, we simulated lithium in carbon nanotube. For lithium in carbon nanotube, the activation energy that the lithium requires to diffuse through the tube is actually negligible at about 0.03 electron volts. Thus, we can conclude that lithium does not need any form of force or interaction for it to move through the tube. Another thing we realized was that for charge systems also exhibit a similar characteristics as compared to the graphene. So it's similar, same for the dimers.
I'm Dennis, the person before me just now was Sean, and so anyway, so basically now we're back to the original model for our project, which is basically the graphene carbon nanotube hybrid. So first of all, we first tested on graphene, then we started on the carbon nanotube, then we put them together as a hybrid. What we found out was that as compared to the graphene and carbon nanotube alone, the hybrid was deemed almost impossible to diffuse a lithium atom through it. We also found out that while I was trying to diffuse through, a certain carbon atom was displaced, and so therefore, because of the displacement, we assume that because of this displacement, therefore, the atom is unable to diffuse through the carbon nanotube graphene hybrid. Right? And it cannot do this under normal temperatures, room temperature, standard conditions. So our conclusion is basically that the dimer and single system are largely similar as when tested in the graphene and carbon nanotube models. They behave similarly, and also changing into a combined structure such as the hybrid, it affects the band structure, which will lead to the high activation energy required. Lithium dimers also tend to make the axis parallel to the carbon nanotube. This is an extra result that we found out, which just make itself parallel to the carbon nanotube because that is when it is in its lowest energy state. And lastly, about charge systems tend to have a greater energy change. So for future, right, we could possibly use a carbon nanotube which a larger circumference for the hybrid, because in other works we found out that the other people who have attempted a similar experiment, for example MIT, they use circumference of the carbon nanotube was much larger as compared to ours, which is basically we were unable to achieve due to low computing power. Yeah. So basically, this is our work.